Hi, my name is Chris Celio. I'm a graduating grad student from UC Berkeley. And today I'll be talking about version 2 of Boom, an open source out-of-order RISC-V processor. And today's talk is going to be purely about academic processor work. So what is Boom? Boom is an out-of-order core. So although I'll give you the illusion of in-order execution to the programmer, it's going to actually try and fill in bubbles as it can by executing instructions as its dependencies are filled. It's superscalar, so it's not just fetching and executing one instruction cycle, but multiple instructions. It's fetching and issuing and executing every cycle for every stage. This implements the RV64G general purpose ISA with enough supervisor support, page-based virtual memory, so that way we can boot Linux or run applications on top of it. It's synthesizable, so we can put this on an FPGA. We can push this to a CAD flow and get a piece of silicon back out of it. And it's open source, so you can download it, play with it, update it, improve it, and give those changes back to us. And that's written in 16,000 lines of chisel. It's also not just one design, it's really a generator. So this is just kind of showing one example instantiation of what you can do with Boom. And to make this easy, this is built on top of the Rocket Chip SoC ecosystem. So Rocket Chip is built around the Rocket in-order core that provides caches, memory systems, debug, privilege support, IOs, test harnesses. So I just come in, and I've taken the Rocket in-order core, and I've simply replaced it with my out-of-order core, and I obey the same IO interfaces. So from the outside system, they have no idea that this is actually a Boom core, not a Rocket core. It looks identical, unless you try and maybe try and get a CoreMark score out of it or something. There's a lot of neat features in Boom. Just as a few examples, it has advanced branch prediction. So this is a branch target buffer that's set associative. With a return address stack, it'll give you an answer in one cycle. There's more complex G-share or a TAGE-based implementation for conditional branch prediction. That'll give you an answer in 3 cycles. And all of those predictors fit in single-port SRAM, so we can fit that very densely on a chip. It does other fancy things, loads and stuff go out of order. You can get all sorts of performance metrics out of this. And as I said, you can synthesize this. It is parameterizable, so this is what, say, a dual-issue Boom would look like, and it's only a few lines of chisel code to describe this. And if you wanted to instead have a 4-wide Boom, it's just a few more lines of chisel. And all of the plumbing, all of the connections of the issue ports, the wake-up logic, the register file, read and write ports, all of that's handled by the generator. So you can kind of play around and figure out what best suits your needs and how much FF4 you want to pay for it. So I'm really happy to announce today that I finally taped out Boom. So this is, there is a silicon chip now that we just got back a few days ago. This is in TSMC 28 nanometer. This is a research academic test chip. So unfortunately for pre-publication rules, I can't show you any cool pictures or really tell you more about it. But today's talk is really going to be not about this particular chip, but really about the process of getting to this chip. So maybe a better title for my talk is Boom version 2, taping out an out-of-order processor with 2 people in 4 months. So this is work from me and my collaborator Pifang. This is her academic research that she's exploring, and so she did a lot of the physical design, a lot of the tool flow, and a lot of the actual hard parts of this tape out. So to give an idea of exactly where Boom kind of fits in the processor space, I figured I'd show Boom compared to a few other processors. So I'll start with the Rocket in-order core on this column. This used to be comparing to Berkeley tapeouts, but now it's supported by Sci-5. It now qualifies as an industry core, which is great because there's not a whole lot of industry open source cores to look at. There's not any open source industry cores, so instead I have to talk about the UltraSpark T1 and T2. Those are in-order mini-thread cores, and so you can get a kind of feel for maybe the difference in lines of code compared to, say, Chisel and Verilog. And I'm comparing against the A9 simply because that's kind of what I've been targeting Boom to be better than for my graduate career. And then, and Intel Xeon is what I just happen to have for benchmarking. I'll let you guys guess how many lines of code you think that processor is. I don't know if a couple Intel guys want to shout a number or not. So here's just to give you an idea of the area, the performance, the frequencies. They're all in different technologies, so you have to do a little math in your head. But and the CoreMark is something that it hits in the cache. This gives you an idea of how fully utilized you can get a pipeline to go. And you know, it's not bad compared to other out-of-order industry cores like the A9. And the frequency is not too bad as well. The other thing I wanted to highlight about this in terms of the core mark per megahertz is that this is just kind of one instantiation of boom that we taped out. If I want to trade away some area or frequency, I can make that number go up. And what I've been able to see is about 5.4 core mark per megahertz is what boom can do if you want to spend a lot more time doing physical design work. Now, why is there a boom v2? Why didn't I get it right the first time? So throughout my grad career, I only had access to educational libraries, and I didn't have access to a memory compiler. So essentially, I had to use kind of analytical models to tell me how fast or how big an SRAM is. And this is you know, OK to get you to a certain level of confidence. But there's a certain point where you start to get results that you really can't trust enough to justify spending a couple months to redesign the entire pipeline, particularly if you have to do a redesign that it's not obvious what's actually going to be the better idea. But in order to do a tape out, we finally got our hands on a commercial tool flow and a memory compiler, and then we could actually really trust that the changes that we were making were the changes that we needed to be making. So today I'm going to talk about what those changes were and how quickly we were able to make them. So to give you an idea of what a 4-month Agile tape out looks like, don't look at the clock frequency numbers. I'm a terrible researcher, so every data point I've changed all of the variables. And also, this doesn't capture the fact that a lot of these points are actually design rule check failures. So there may be shorts or other things that you can't actually manufacture them. But we started out with, once we had the flow up, trying to figure out exactly what it is that we have on our hands. And we came up with about 4 critical paths that we thought were important to go and fix. And so then we walked away for about 4 weeks, and then we came back with these fixes. One of them wasn't fully functional, but at least it was enough of a fix to see if this was something that we could analyze and justify further work on. So we then started to play around with this. The open holes, by the way, are just synthesis runs. Those are a few hours. The full holes are place and route, which is like a day. And then once we were content that we were doing the right thing, we went away to kind of finish up our work. And then at the beginning of July, we could then do the sprint on the physical design and focus on the smaller fixes. So this is what Boom V1 looked like. This is a short pipeline inspired by like the MIPS R10K, the Alpha 21264. They have some nice papers that explain what they do every stage, so I could follow that as an academic and try and recreate that. However, that was the 90s. They did a lot of full custom design, a lot of dynamic logic. So there's things that they did that I can't really do now. And there's other, you know, so a few other things, you know, very short front end, decode, rename, and dispatch. We have a single register file that's floating point and integer. And we also have a unified issue window, which makes life easy, but it means that you now have, you know, multiple issue ports off of one issue window. And if we're trying to do a synthesized design, that's going to be kind of hard to do. So this is what we started with. And then we identified those 4 critical paths. So to dive into one of them, this is the Boom version 1 front end. So the idea is you have fetch 0, where you set up what the next instruction address is going to be. And then in fetch 1, you're going to actually fetch your instruction. And you're going to have your little BTB make its prediction. And you're also going to access your conditional predictor in parallel with the instruction access. Now, unfortunately, that means on the fetch 2 cycle, you have to actually figure out where are the branches, what are the targets, then do we actually want to take the prediction, then go through the PCMux, and then do the hash. So this is obviously a lot of work to do in one cycle. So we're going to fix that. And we're going to make a couple changes. The first is actually in the BTB. So this was a fully associative, fully tagged BTB. We could only do about 30 entries. So instead, we decided to put that into, and also flip-flops. So we decided to put that into SRAM, make this solely associative, partially tagged, so that way we could have 200 entries in the same frequency. We then also moved the hashing to its own stage, and then we also moved accessing the branch predictor in parallel with actually computing where the branches are and where their targets are. And so we've simply added an extra stage to this pipeline. And this actually ends up not being too big of a deal, because even though your branch predictor now has an extra cycle, your BTB is going to capture a lot of that anyway. So you're not paying this penalty a whole lot. Here's what our first place and route job looked like for the register file. It should only take up about maybe 15 or 20% of the area, and it's blowing up. This is what happens when you try to do a 10-port register file. The synthesis tools don't like you. So this is one problem, is we need to figure out how to address a 10-port register file. The other part is that we are trying to do selecting which instructions we want to issue, and then read the register file in the same cycle. So we're going to have to split that up as well. So to cut ahead a little bit, this is essentially what Boom v2 looks like. So we ended up splitting this issue window into 3 pieces. So we could have 1 issue selectors on these guys and then 2 on the ALU. So that only took about a day of work with the power of Chisel. We also split up the register file, so that way we could fully synthesize the 5-port floating point register file. And then the integer register file, we could lose a read port. And I'll talk a little bit more details of what we had to do to actually get that to place. But that was something that we could then have fewer registers to make that a lot easier for us. And that was about a week of work, and that was mostly just because you now have a lot of complication of moving integer registers to floating point to integer. Those instructions get a bit more complicated. We also fixed a critical path in the rename, so that's added a stage. And as I said, it took about 3 weeks to do all of the lengthening on the fetch cycle and adding a new BTB. So let me talk a little bit more about how we dealt with the register file. The problem is that the foundries are only going to give you a memory compiler that'll give you a single port or a 2-port memory. Companies, at least some of them, will just build and handcraft their own multi-port register files. Other companies will just synthesize it. As an academic, there is only 2 of us, so we didn't quite have the resources of a company. So we had to come up with something a little bit easier for us. This kind of shows exactly what the problem is with you trying to synthesize. So if you have, say, 70 registers and they're 64-bit registers, each register is giving out a wire that then has to go to the read ports. So you end up with about 5,000 wires in congestion. And what the tools do is they say, all right, let's just put wires through each other and short them together. I'm sure that'll do it just fine. So unfortunately, all these X's are all of these shorts. So we can't actually, even though it'll go fast, we can't actually, well, we could synthesize it, it just wouldn't work. So what we did instead is we black boxed the register file in Chisel, and we wrote some hand Verilog at the register file bit for the specific bit. So we said we want to instantiate out of the standard library this specific flip-flop, this specific mux for the write ports, and then 6 tri-state buffers for the read ports. So now we could actually just lay down. We could then pre-place these cells throughout the chip and then let the routing tools lay over the wires across each of the bits. So that way we reduced the number of wires by an order of magnitude. So kind of just said another way, you need 18 wires coming into and out of every bit in your register file. So through this technique, particularly using the tri-states, we could dramatically reduce this. And since you don't want 70 guys driving one tri-state, we had to use hierarchical bit lines. So this is kind of our before and after of going from Boom v1 to Boom v2. And this particular version of Boom v2 is what we taped out. OK, so what were the results of this? I'm talking about fixing critical paths and making the BTB bigger. So how did the performance change? So this is maddeningly difficult, actually, to compute and kind of figure out because, as I said, I'm a terrible researcher. We changed all the variables as we went along. And it turns out that a lot of this work was really just about the design rule checks, about coming up with a version of an out-of-order core that you could actually push through a tool flow and get something that works out at the end of it. So we did try our best to do kind of an apples-to-apples comparison where we actually backported a lot of our physical design work to Boom v1. And what we saw is that we got about a 25% decrease in the clock period. Now, there's a lengthening in the load use delay, so that caused us, at least on CoreMark, to lose up to 20% just because of that increased path. That's a fix that we know how to fix that. We just need to go and do it. If we had another month for the tape out, we would have been able to have addressed this. So it seems like, OK, maybe you went faster to get the same performance. But as I said, this is really about fixing all the geometry errors and getting a register file with 9 ports that you could actually tape out. So from that point of view, it's infinitely faster. I figured I'd talk a little bit about how at Berkeley we espouse agile hardware development and kind of provide my thoughts on this. I feel pretty confident now that I can say that we figured out how to make Agile hacking very quick. It's been pretty impressive that from Chisel, I can make a change and push it through the compilers. It goes from Chisel to Verilog. I can compile that Verilog to Verilator. And then I can run through all of the RISC-V tests in parallel in about 6 minutes. So that's a pretty fast to make changes. And you can make some pretty quick, far-reaching changes with Chisel, with the design as well. And with the generator, you can make some very late binding decisions. So this was really, really pretty nice. We could make changes to Boom and kind of convince ourselves that a critical path really was a true critical path because we could change how many function units we had or how many issue ports that we had. However, this kind of only really works in terms of the agility if your changes are small enough to not really affect the physical design. So this is still kind of a bottleneck that has to be addressed. For starters, it takes maybe a half day, a full day, just to get an answer from the physical design to see if you screwed something up. But even then, there's still a lot of value that's provided by manual intervention. You can't just kind of give a computer and let them give you a good answer. And even then, the reports are maddeningly difficult to reason about. I don't think obey the laws of thermodynamics. If I remove logic, I would expect my processor to get faster, and sometimes the report says it got slower. So that's kind of hard to give to a computer and let them figure this out. So at least not yet. We can't walk away from a week and come back from our vacation with 7 good design points ready to tape out. The other bottleneck here with Agile hardware development is I can write bugs now even faster. And with an out-of-order core, it's even more difficult to reason about exactly what's going on at any given point in time. It's maybe doing something wrong just because it's speculated that it should do something wrong, and don't worry, it'll fix it up later. So this has been a challenge, something that's kind of ongoing work. We have some papers that are in flight on how we've kind of addressed this. In terms of future directions for Boom, this has given us a pretty clear idea of exactly where our weaknesses are and where what we can do to improve the IPC, the area, the frequency, and the quality of results. So I don't want to give any sort of promises or specifics, but just to say we're aware of what things that we do want to change. For me, I'm graduating. I'll be turning in my thesis in 2 weeks, and I'll be joining Esperanto Technologies. If you're watching this on YouTube, go and see Dave's talk from yesterday about exactly what Esperanto Technologies is looking to do. We're on a lot of working groups in RISC-V. We're very interested in making sure that RISC-V is a great ISA and that we grow it into a great ecosystem. And as part of that, we will be continuing to maintain and support the Boom open source ecosystem. So it's not, Boom's not going away. And also, if you found this talk interesting or exciting or you'd like to do this too, we are hiring. So do come and talk to us. A lot of us are in the Green Church today. And the final thing I want to say is, in order to do a successful 2-person tape out in 4 months, my advice is have an entire village of people behind you. That makes it a lot easier. Whether it's the RISC-V ISA that completely gets out of our way, it lets us do our job. It comes with a certain amount of tests and programs and Linux and stuff. That's been a really great thing that we don't have to focus on. The Chisel hardware construction language allowed us to be very productive and make changes very quickly once we realized that we needed to based on the physical design aspects. And then there's some cool things with Fertile. So we've actually opened up the Chisel compiler to have an exposed intermediate representation. So people can write compiler passes to do things like black boxing certain aspects or adding in scan change or something. And finally, there's the Rocket Ship platform, which has been built by Berkeley and maintained by Sci-Fi. This allows people to kind of get into a RISC-V hardware development, extend it with their own sliver of innovation, and then have something that they have some reasonable confidence in. So I'd like to thank everyone that's been involved in that. I think with that, maybe I have time for a question or two. Thanks. So the question is, have I thought about partitioning the out-of-order core into pieces so that way we can do more partitioned physical design? The hard part is that there's quite a few aspects of the core that have a high fan-out. And so that makes it quite a bit harder to do that. We certainly have been thinking about how we can do this in Chisel or in Fertile, kind of describe exactly how things should be floor planned or what their adjacency should be. But we haven't really thought too seriously of going further into how to give better floor planning and hierarchical design. Yeah, the fan out is really, really pretty painful. Just things like the data coming back from the data cache, or maybe like the branch kill signals, those types of things. What are my thoughts about performance what? Verification of performance. Yeah, it'd be nice to have a performance verification suite. What I use is for like a lot of my branch prediction stuff that I was doing with the front end. I do have a set of micro benchmarks that I know what the branch prediction accuracy should be, so that way I could verify that I didn't introduce a bug there. For CoreMark, that was something that I could put to Verilator and get a quick CoreMark score out of just to see that I didn't break something in the pipeline, or at least if I did break something, I knew I could catch that fairly quickly, like the fact that I added an extra cycle in the load use delay. There's not really a great set of benchmarks that are in the order of a couple, sub-million cycles. So usually if we care more about performance, we'll just put Boom on an FPGA and then run it, which is not really what you want to be doing here. So it would be great to have more infrastructure for, maybe even a shared infrastructure of performance microkernels that we trust are adequate. So for example, I guess yesterday was the microprobe talk on these kind of auto-generated benchmarks. That would be an interesting thing to look into. In slow, I believe it was 650 megahertz slow, maybe 700. I guess I didn't say it. In the post place and route, our measurement of FO4 was 50 FO4, and the post synthesis was 37 FO4. So we need to, still a lot of work to close that gap. So we do know of quite a few things we need to do on the physical design to make the place and route better. All right, thank you for your time.